Hello, algebra students. Today we're going to talk a little bit more about exponential growth and decay. And we're going to start with a couple of graphs, and then we're going to look at some applications with both population growth and compound interest. So let's start with just the graphs. So let's say we want to graph these functions and tell whether or not they're growth or decay. Well, telling if they're growth or decay is pretty simple. You're just looking at the value that's being exponentiated, and if that value is less than 1 but greater than 0, it's decay. If it's greater than 1, then it would be exponential growth. So 1/12 is less than 1 but greater than 0. So this is exponential decay. All right, so telling if it's growth or decay is really that simple. And next, to graph this, we're going to graph a small table of values. So we'll make our little XY table. And I'm going to pick -1, 0, and 1 and plug that into the function to get y values. So we have 1/12 to the negative first power. That would be equal to 12. 1/12 to the 0 power is equal to 1. And then 1/12 to the first power is equal to 1/12. And just those 3 points should be sufficient enough for you to see the shape of this graph, the general shape of this graph. So now let me make my axes. So there's my x-axis, there's my y. And we'll say this is at -1, this is 0, that makes this 1. And we're actually going to have the y-axis go up by 2's. So 2, 4, 6, 8, 10, 12. So at -1, the function is at 12, so we're plotting the point -1, 12. At 0, the function is at 1, so it drops all the way down to here. And at 1, the function is at 1/12, so it's getting pretty close there to the x-axis. And then you want to connect those points with a smooth curve. And you might be tempted to have that function cross the x-axis. But remember, this is an exponential function. It has an asymptote at the x-axis, meaning it's going to get closer and closer, but never actually touch the x-axis. And there's our graph. All right, for the second example, 1.5 to the x power, this is a growth function. Why is it a growth function, you might ask? Well, because 1.5 is bigger than 1. And we'll do the same thing. We'll make a small table of values to graph the function. I'm going to continue using -1, 0, and 1 for my tables. So if I have 1.5 to the negative first power, that is 0.6 repeating. Now if you guys don't know that offhand, that's okay. You could do that on a calculator to come up with 0.6 repeating. 1.5 to the 0 power is just 1, because anything to the 0 power is 1. And 1.5 to the first power is 1.5. So we've got 3 points we can plot. And let's graph this. So there's the y-axis. Here's my x-axis. I'm going to put -1 right here, 0 here, and 1 here. And the y-axis is actually going to go from 0, we'll put 0.5 right here, 1 right here, and 1.5 up here. So at -1, we're plotting the point 0.6 repeating. So -1, 0.6 repeating. It's roughly around here. And then at 0, we were at 1. And at 1, we're at 1.5. So it looks kind of linear, but it's actually an exponential curve. All right, so for number 3, again, table of values. We're going to use -1, 0, and 1. 7/2 to the -1 power is 2/7. 7/2 to the 0 power is just 1, and 7 halves to the first power is 7 halves. Okay, now let's make our xy axis. Whoops. And let's put -1 here and 1 over here. And we'll have the y-axis will go up by, let's have it go up by ones. 1, 2, 3, 4, 5. So at -1, the function is at 2/7, which is like 0.29. So it's pretty small. At 0, the function is at 1. And at 1, the function is at 7 halves, or 3.5. So it's way up here. And then connect those dots with a smooth curve, and you have your sketch of an exponential function 7 halves to the x. All right, last graphing example. Oh, we forgot to say that this here is growth. It's going up towards the right. It's growing to the right. And in fact, we can say from the start here that this one is decay because 0.8 is bigger than 0 but less than 1. So it is a decay function. So when we graph it, we should see it going down towards the left, kind of like the first graph that we did. All right, let's make an XY table. .8 to the negative first power is 1.25. 0.8 to the 0 power is just 1. And 0.8 to the first power is 0.8. And you can see as we go down this table, the value of the functions are going down. So it is indeed a decay function. Okay, let us plot our values. All right, let's put -1 out here, 1 out here, and go up by 1 every 2 boxes. All right, so at -1, we're at 1.25. -1, 1.25. At 0, we are at 1. And at 1, we are at 0.8. Now again, this looks linear, but it's really curving downwards here because it's an exponential decay function. All right, so hopefully that's enough examples for graphing. On any sort of a summative assessment on this standard, you would also have access to a graphing calculator, which you can also use to help yourself graph these functions. But let's look at some population growth. So the number of bacteria in Y in thousands in a culture can be approximated by the model Y equals 100, 1.99 to the power of T, where T is the number of hours the culture is incubated. Now tell whether the model represents growth or decay, exponential growth or decay. Well, we know that 1.99, that's bigger than 1. So this is a growth function. And you can kind of think about that, and it should make sense, because if we plugged in 1 for x, we're multiplying by 1.99. If I plug in 2 for x, we would be multiplying by 1.99 squared, which is 3.96. So every time x increases, we're multiplying by a bigger and bigger number. That's why this is exponential growth, because it's growing as x increases. That multiplier is growing as x increases. Okay, identify the percent increase or decrease in the number of bacteria. Well, we could rewrite this as 100, 1 plus 0.99 to the x power. And the reason why we rewrite this like that is because it is easy to identify then that the 0.99 is the percent increase. This is a 99% hourly increase in bacteria. Alright, to estimate the number of bacteria when the number of bacteria will be 1 million, I will have you guys use a graphing calculator or Desmos. And what you're going to do is graph 100, 1.99 to the x power. And you're going to graph the line y is equal to 1 million. And then what you want to see is where do these graphs intersect. Unfortunately, my recording software doesn't allow me to switch screens, but I will sketch a graph of what this looks like. It would look something like this. And you'll see an intersection point right here. And the value of that point is 13.4, 1 million. And that means that we would expect the bacteria to reach 1 million after about 13.4 hours. All right, lastly, we are going to do a couple of compound interest problems. The first of which we have 2.25%. It's compounded quarterly. And we also note that the time will be 5 years and the principal is 1,250. So let's just label all our variables. We have P equals 1250. We have R is equal to 0.0225. And we have the number of times it compounds is quarterly, that's 4. And it does this for 5 years. And then we're just plugging into the compound interest equation, which was given in the last video, but here it is just in case you've forgotten. And we're plugging all those values in. So A equals 1250, 1 plus 0.0225 divided by 4 to the power of 4 times 5. And the most common mistakes I see on questions like this is just people plugging it in wrong on your calculator. So be very careful when you're plugging this in that you've got everything correctly in the exponent and in the parentheses, because that's really the biggest way to make a mistake on this question. And if you plugged it in correctly, you should get 1398.40. So that is how much money it is worth after 5 years. Fairly impressive, made over, close to 150 bucks, just letting the money sit there. For this next one, we have the same principal, but now the rate is 1.25% or 0.0125, but it is compounded daily. So there's 365 compounds a year. And then the time is still 5 years. And then we're plugging all of that into the compound interest equation. And when doing so, we should get 1330.62. Alright, so the goal of this video was to just expose you to a few more types of problems that you can see with exponential growth, decay, graphing, population growth, and most importantly, compounding interest. And tomorrow, or in the next video, for you guys watching on YouTube, we will talk about the natural exponential function. Until then, guys, see you later.